Hey guys, this is Code Metaphor. So, what I thought today, I called one of my friends, and my friend is Abhishek, and he will discuss a topic today. So, we will see and ask him which topic he want to discuss to clarify our concepts and see what he wants to say. So, Abhishek, here you go. So tell us which topic are you willing to share with us and get us more understanding in terms of how to design the code and how to write its code. Yeah,
Absolutely. I want to thank Kaz. So thanks a lot, Kaz, for bringing me here
perfect. Okay.
for this video. So the topic that I had in mind in order to discuss would be the length of a binary tree.
Okay, so you mean that you wanna show the first binary tree a little bit, and then you wanna tell us how to find the length of the tree?
Yeah,
Okay,
yeah,
so
that's
let's
what I
see.
had in mind.
Let's see. And let's talk about it and see how can we naturalize it and try
Mm-hmm.
to understand it completely. So if somebody looks at it and say, "Hey,
Mm-hmm.
I know how to code this,"
Right,
right? We
right.
should be very clear. So let's go ahead. Yeah, go ahead. So here is
Absolutely.
there are your pens and stuff. So anything you pick a pen
Mm-hmm.
and go ahead.
So let's start with the binary tree itself.
Yeah.
So first, let's create a binary tree. So in a binary tree, like you can have maximum of two nodes, and for any given tree, so you have a root node. So
So you have to
uh,
press it, like if you want to make a node you have to press the mouse, and this is your A, this is your
okay,
root. Okay,
okay.
good.
So yeah, so now I think we are good to go. So
Yeah,
this is, so I'll call this the root node. So I'll abbreviate it in R,
yeah,
and this root node, let's say it has two childs. Uh, so so we have this one node and we have this another node,
excellent. Yeah,
and again, like this has like two different child. However, this has only a single child. So let me go ahead and write that,
so
and then
so
this has like
what's
another
going
single.
what's going on here? So we have the root, and then you have the children, right? So what about the rules that we have, greater than, less than? Is this like a binary search tree, binary tree, like which one you are trying to say?
Absolutely. So, like, there are a lot of different trees, but for a binary tree, so it simply needs to have uh, a maximum of two nodes. So it can have, so given a class node, so
Two
let
child
two
nodes.
child nodes
Yes,
exactly. So
okay,
one we call it as a left node, and the other we call it as a right node. So
okay.
this could be any tree, so it doesn't have to be a binary search tree
Mm-hmm.
per se. So
Right.
over here, so in a binary, because it's in a binary search tree, you order the nodes based on their values, so that it's very convenient for you to search. However, we can have any number of values inside these nodes. So, and this is what, so if I have something like 10
1,
over
2,
here,
let's suppose.
and
Yeah,
let's say, yeah,
10,
just a
11,
one.
10,
So this is
11.
not a binary search tree, but yeah, this is definitely a binary tree that
So
we
we
have.
can, you mean that in a real use case, we can have a binary tree,
Right.
arrange our data
Mm-hmm.
in this case, right? And what do you think, why do, like, many of us have this question, why do you need the binary tree? Like, we perform certain operations, data efficiency, what's going on here?
I mean, that's a really good question. So that kind of depends on like the use cases that you have. So in a lot of like, so we have the arrays and we have the lists.
Okay.
So
Mm-hmm.
this is pretty linear. So I guess like so when you try to move forward or backward, so you are, so this basically the decision point is fixed for you. So you can either move forward or backward, but with you know about the if and else conditions,
So
right?
means iteration. If I'm iterating the array, either I can go forward,
Forward
either go
or
backward,
backward,
and they are in the same memory location.
right?
So we talked about it before also, that these nodes that you have, these are in different memory locations, having the
Absolutely,
pointer to each other, right?
absolutely.
So that's how.
Mm-hmm.
Um, and then we talked about the complexity of it also, that why it's much more efficient. It's order of log n if you want to do something, right?
Right,
We can cut a
right.
lot of processes, right?
Right, right.
Okay.
Yeah, so if your like tree is balanced and so you can cut. So basically you don't have to go through each and every other node. So let's say like this was a decision point, either go left or go right,
Mm-hmm.
and then you selected a left, so you are just skipping all these right nodes and again. So this helps us. One example of this is like the binary search tree. So where
Okay.
we get the order of log n search time on the nodes
Much
themselves.
better than other
Much
algorithms,
better
right?
than going through the unsorted array itself,
Okay.
so that would be like going order of n, because like going through n elements in order to find a single element.
So like um, we talked about binary search, right?
Right.
We find a value, we cut, and we cut is order of log of n also,
Hmm.
right?
Right.
So that's also like kind of similar way. We are cutting the processes every time,
Absolutely.
right? But that's an assorted array. This is a constraint of it.
Hmm.
So okay, great. So now Abhishek, tell us that. So what is the height here?
Yeah.
What height we have right now in this
So
tree? What is
so
the
so what
height?
do you see? So we have this height. So we have the root node, and so ideally like some books say
Mm.
that the height of this tree is 1 2 3, the depth. Some may say it is 4 1 2 if you count the root as well,
So
so
let's
1
just
2
talk.
3
Let's take
4.
it four. We want to make it
Yeah,
generalized.
yeah.
Yeah.
So the height of a binary tree is like the maximum depth that you can travel to the child node. So over here, like if you
Can you
travel
get
left.
another color, please?
Absolutely.
Just get a red
So
one or something.
yeah,
Yeah.
so
Okay.
so if you go from the root node towards your left child, if you travel this, then
Mm-hmm.
you have two options. So if you travel this or the right one, so in either way,
Okay.
you reached a maximum depth of 3, including the root node.
Okay.
Even if you go on the left part, it is still depth of 3. However,
Okay.
when you're on the root node, and if you selected a right node,
Yeah.
and now basically this has only one node, so it is pretty sequential, and over here also you have pretty sequential. And once you reach the leaf node is a node which doesn't have any children, so it's safer to say that the children nodes are empty or null. In our case, like they don't have any reference to
No.
another
Yes.
object,
Yes. Yes. Okay.
so this is a null node.
So just sorry. Just one question. Now, even in a real life, when we look at a tree like this, like not thinking about how to code it right now, but before you know that it's important to do it on paper first, right? So even in a real life, even if I'm not coding or anything, I might say that okay, I will start from root, right?
Mhm.
Then let's suppose if I come here, I will come here, and I will come here, right? Even in a real life.
Yeah.
Yeah. So now what what will tell us, like, because there are multiple routes, multiple children, what will tell us that hey, this is, you will be assured?
Right.
Yeah, I tell them the neuron work. What's your
Right.
neuron saying in this one?
Yeah. So what my neuron says is, like I mean, like over here, like we can visualize this tree, right? So,
Yeah, just visualize it.
but
Yeah.
what happens like if there are like millions of nodes?
True, true. Okay.
So you would not be able to, you know, conceptualize what's the height of the tree, right?
So
Like,
what's the way? What's the efficient
so
way to
what's
be
the way? So the best way is like to explore all the paths.
explore
So
all the
so if
paths?
you explore all the paths, so if you from
Okay.
over here, so you went left and right, and so now, so once you, so let me get ahead this one. So you're on the root node, you went towards, you traveled to the left node,
Okay.
you
We
came on the left node,
So
and
how
then
do you
again.
decide that? Which way you want to go? What is the decision point, or it's up to us?
So it's up to you. So
Okay.
the idea being like you don't travel the same route again and again.
Okay,
So
great.
so ideally, like what you would do is like the best way would be like go all the way to the left until as long as you can possibly can, and
You know
once
what
you
I
have traveled left, then go towards the right.
so what I do usually in a tree, as my use cases, based on my business need, I decide whether I should go left and right
Mm-hmm.
based on my use case. This is one way I do
Right,
all the time in my
right,
military,
right.
right? So now tell us this thing. Now, if I go from A to 10,
Mm-hmm.
from 10 I go to, let's suppose this is 13, right? I
Yeah.
go to 13. Uh, Now explain to us like you are thinking, because yeah, of course we have one model in our head, but your model may be clarify our concepts. What do you think now?
So in this case,
Now here you, for example, to clarify it for everybody, draw it, like give us in here that okay, I went from this to this to this, and that's how I got it. This is
mhm.
how I get, this is return value, something like that, right? Now go ahead.
So let's start with the root node. So over here we have
Mm-hmm.
the root node. So we were at A, the root. So let's call it R. And over here we have the value as 1. So this is fixed, right? You
Okay.
always start with 1. So you
Great.
always know that if the
Okay.
root is not null, then that means you have a height of 1,
Okay, great.
right?
Okay.
Now I want to explore like what is the actual height. So now I have two possibilities, go left or go right.
Okay.
So I would always, so now for the sake of simplicity, I would always start from a left if the left
No
exists.
worries. Go ahead. Okay.
So so then I travel to the left part, so I reached the node with the value is 10, and I know, so I came from 1. So when I came to the 10,
Yeah.
so I can store that, okay, so this is 1 plus 1, which is 2, right?
Okay, great.
Right,
Okay.
and again at 2 I have two possibilities, go left or go right. So what I
Okay.
would do next, so the next part would be again go left if you have both the
Okay,
possibility.
great. We go to 13.
So yeah, so now we went to 13,
Mm-hmm.
and in this case, so now the height is 2 plus 1, which is 3.
Excellent. Okay.
And then for 13, now since we are at 13, we check, does the left exist? No, it does not exist, it's a null node.
Mm-hmm. And if the right exists or no.
Yeah, so can I go to the right node?
Yes,
No.
yes, yes.
So for 13, like this is null.
Yeah.
So
Okay.
in this case, like this was the maximum that we reached so far, right?
Excellent. Okay.
So let's say like we have a variable which is like the max height, right?
So okay, we need one
Yeah,
variable.
something to store like what has been the most traveled part so far. So we
Excellent.
can initialize this with a 0,
Mm-hmm.
and so this would be a max height. So now let's assign this like, so you always updated it every time you reached a new node. So
Okay.
with the root node as 1, so you update, okay, max height was 0, so let's update it to 1. Then with 10, oh, it's 2, so again let's
Okay, great. That's fine. Now,
so
what
now we have
happens
it as a
now?
3.
Now, we have a max height right now from left side.
Right.
Now, it seems to me that when we came from A to 10 to 10 to 13, right?
Yeah.
Now, I also have to check A to 10 to, let's suppose, T,
Mm-hmm.
right? Now, I told them the concept, I think this was used here, the backtracking concept,
Right.
right? So I think we are using here
Mm-hmm.
something we are doing with a stack to make sure that we can go
Exactly.
back, right? And
Exactly.
I'm sure you were telling us this the next thing.
Absolutely.
So yeah,
So yeah,
explain. What do you think about that?
so yeah, that makes a lot of sense, like the backtracking part, because like you don't always want to start because you have to keep track, like you travel left, left, left.
Hmm?
So again, like there were a million nodes, so you don't want to again start from, oh, what was the last one that
So
I did?
I can, from 13, now
Right.
I can go back to 10.
Right. So let me go ahead and so I guess like Cass, you already explained the concept of backtracking.
I did, yeah.
Yes,
Backtracking, like I explained to them that, okay, I
absolutely.
go from A to B to C. How can I go back to B or to A,
Absolutely.
right? So,
So
okay.
we utilize a data structure called stack,
Yes.
and once we visit a node, we update what has been this, and add it to the stack to in order to, so we only explored one path of it.
So the purpose is just I'm adding to stack just because I
I
want to
want
come back to it.
I want to re-explore the other path.
So I was telling them the concept of this one. This one. So if I press this, it's removing this.
Right.
So I was telling them this is exact use of a stack or double-ended queue we can call it because there are double here, right?
Yeah.
So okay, great. So we are in A right now. We pushed it to the stack. Then what happened?
Pushed it to the stack, and again then we had two options. So then we went to the 10,
Right. Okay. We
and
pushed the
then
10 in
again
the
we went
stack.
to the 13 part.
Okay.
So we did it for 13. We got the height as 3.
Exactly. Then what happens when there is a null thing?
Right.
When are you gonna stop?
So when for 13, like, we had the left and the right as null, right?
If left is
Right.
null.
If left is null, so what you do is, so you pop so now the other path that remains is like the right path of
Okay.
it, and then the 13 is
Okay.
explored,
Okay.
right? So what you do next
So what's
is,
the next step here?
so the next step would be for 13, uh, so the right path. So in this case, like, the left does not exist, but the right also does not exist. So what do we do here? So we are done exploring 13.
So you wanna just pop it from here.
So yeah, so now there is no other option.
So if we pop it, that means we lost it.
Yes,
Yeah,
you
that's
lost
what I
it.
wanted to note to them that if we popped it, that means
Right.
this node is done. You can just cross it as you like. You
So
can just
let's cross
it. Yeah.
this. So this is done. So now we are still left with A and 10 in the stack.
So okay, great. Now
So
what we're gonna do?
now the next thing that you would do is, in the stack. So now
The
once you come
pointer
back
goes
to
to
the
the
now
top
once you
one.
come back to the
Yeah.
stack,
Ah.
so you already know that you have explored the left part. Now go to
Excellent.
the right
Okay.
part.
Great. Okay.
So over here we have a T. So in this case, so let me go ahead and use
We
an
have
eraser.
we have to insert the T. Push the T. Oh, that's a big. That's a, let's get this pointer and you can get the red one. Okay.
Yeah.
Mhm.
So let's go ahead and,
Push the T.
you push the T.
Okay, we push the T.
So
You can put, yeah, push it here. That's fine. Wait, let me give you this one. Okay, so now we got the T. Then what happens?
so now we explore the path for the T. So we have the left and the right again.
Okay, okay.
So when we started with the T, we found that left does not exist, right? And the max height is
The
still a
right
3.
does not exist.
And so from 10 we got 2.
Exactly.
So T also has a height of 2 plus 1, which is 3.
3, so we don't
So we
change the
don't
max height.
update the max height
Okay,
yet.
great, excellent.
So
Okay.
this is still T.
And so now to my understanding, we are just gonna take a pop T and then because 10 is done,
Yeah.
we're gonna pop the 10.
10. So now
Okay.
all the paths are explored for 10.
So 10 is done, and
Absolutely.
because in stack the pointer comes to this one.
Yeah, and now we explore the right part of A.
Okay, so now the same process goes here and the max will be
Right.
updated to 4.
Absolutely.
Okay, okay, great, excellent. So guys, you saw that how a binary tree, the height, maximum height of a binary tree is 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 used, and I think we can use also like recursion is the same thing, but we didn't discuss recursion. I don't want to touch that topic. So they can use stack, with the help of stack they can do the
Yeah.
maximum height.
Yeah.
Okay, so now, so what's the complexity here? How can a student or somebody who's in the interview knows like, okay, the complexity? So usually what I explain, so here is that if I have an x square function, right? This is a simple machine that I have. Actually, it's a machine, right? So I have a y is equal to x machine. I give him a value of 1, it give me 1, give me 2. Every time it doubles. So I
Right.
have a graph
Mm-hmm.
in here that goes like this, right?
Right, for an x square.
For this is order of n square, and this is my graph for,
Y is equal to x.
yeah, this is y is equal to x, right? Now here what happens? Because I know from y is equal to x squared that this is like this.
Mm-hmm.
Now how are we going to understand this thing, like the complexity?
So before we like discuss like the complexity, so first let's define what is x in our use case.
Excellent. Okay.
So
Great.
so what is X over here?
Hmm.
So we have this tree structure that we have, right? And the only thing that we are given is like the root of the tree. So
So yeah, we
usually,
can also like even in the next video when we discuss we some other time the complexity and more topics about it.
sure.
But you can tell us like we understand it's log of n, right?
So ideally, like if you just explore one path, so that is like order of log and but it is usually order of log n when the tree is balanced.
Okay, so the idea that the point is balanced.
Point is balanced. So you
Okay,
can have a tree that is skewed,
just
so
like a list.
just like a list. So this is a tree.
Okay,
So all the
okay.
left part are so this is basically a list, but this won't give you a
Excellent.
log.
Okay, so we have a log of n complexity for binary tree, balanced binary tree.
Balanced binary
Okay,
only for just going from the
okay.
root to the
Excellent,
child node.
excellent. So I was also thinking, Abhishek, that
And but the thing is, like with this, so now over here we are exploring all the paths, right?
mm-hmm.
So basically what happens, so when we say log n, so that is basically like the height of the tree, right? So that is like,
Okay,
so
okay.
log n over here is like n is all the nodes of the
Number of
tree,
nodes, number of
number of
nodes.
nodes. So
Okay.
in this case, like so when I started the video, so I told you that the only possible way when you have millions of nodes is going through each of these nodes one by one, going through each of these paths one by one. That means that
You
we
have to
are,
go. You
yeah,
have to visit.
so we are covering all the paths. That means that we are covering all the
Yeah,
nodes.
because even in real life, I mean, if I have a big tree,
Yeah,
I must go on each route.
right.
I must say, okay, let me check this one, let me check this one. But here is now another important thing that I was explaining that like a binary tree, very efficient, very fast. We are always concerned about data. Data is the main thing, and we want to access it as fast as possible,
Hmm.
right? So now, for example, I have a customer data
Yeah.
that I can I cannot hit a database every time.
Hmm.
So I might just put my customer data in a tree format, do my operations, and then get rid of it,
Right.
right? So
Right.
because it's going to be
Yeah.
very expensive, the CRUD operation is going to be expensive
Hmm.
on the if I access the database times, and then the
Right.
cache and other systems are another big advanced topic that we
Right.
can talk about.
Right.
But so yeah, Abhishek.
So in this case, yeah, so if you explore all the paths, so over here the time complexity, like you're visiting all the nodes, so it is order of n.
Oh, okay, okay. So if it's visit every node.
Every node. So we are visiting all the nodes. So
Okay.
this over here, like we don't get a log n. So
Yes.
because we are traversing all the paths, so now it is order of n. So we traversed all the paths
Yeah, because
and
we have n nodes getting to every n node, so the
nodes.
complexity
Yeah,
is n.
exactly.
But if I'm searching for a number, that means my complexity will be log of n,
Right.
right? Because I'm
And
cutting every time.
some newcomers, some people might have a question like, okay, so you are revisiting nodes the second time
Hmm.
for exploring the
Yeah.
second part.
Yeah.
So even if that's the case, so let's say like there were X nodes and you visited let's say 2x nodes. So again over here the time complexity is still on order of x, like you didn't square, so this is just a multiple
Hmm.
2x, so
Okay.
again this is an order of n
So we were,
approach.
yeah. Thanks, but we were also discussing the like the pre-order, post-order, in-order traversals, But I just explained that don't worry. If somebody tells you to print me A 10, this, and everything, so we use a stack, right? So and then the stack, the accesses, because we know is the top element. There's a constant access. We
Yeah.
don't even have to worry about that. This happens in a constant amount of time.
Mm-hmm.
Yeah, the space is there, but we have a speed in here, right?
Yeah.
So Abhishek, yeah, that's thank you so much for explaining to us the concept of the tree. And guys, I hope you guys have understood this whole concept of what Abhishek also explained, how we can go through all the routes and how why is the complexity and what happens if a tree is skewed, and more questions are gonna come. So, but the most important thing I explain is that Abhishek, that this is not going to be useful until and unless you think about it. Yeah,
Absolutely.
so I tell them draw it, put it on paper, make your conditions, make your decision points, then jump to the code, right? So, guys, that's it. Abhishek, thank you so much.
Thanks,
And
thank you, thanks guys for having me.
maybe I will invite you for another topic. You can give us a more practical
I would
approach
love
to
to.
this. Okay, great. Thanks a lot. Have a good night, guys. Bye bye.